Directly measure. No, not exactly direct reaction process. So is it a direct measurement or an indirect measurement? Why the name is there infrared? Why not anything else? So first of all, it will only analyze your gas, okay, and that to be all heteroatomic gas molecules. Heteroatomic gases molecules means homoatomic means oxygen. Okay, heteroatomic will be your CO2, methane, everything for that are different atoms, that is heteroatomic. So it will never analyze your oxygen or anything. Got it? And another thing is that all the heteroatomic, they absorb infrared radiation. You got it? After the absorption of infrared radiation, each molecule will, suppose 10 molecules are there, and they will absorb, for example, I'm talking about 5 to 7 infrared radiation they will absorb. Now, if the molecules get increased to 20, so that absorption will be directly proportional to the infrared absorption, means the molecule number. So if it is 10, then for example infrared absorption will be 10. If it is 20, then infrared absorption will be 20. So that way the machine measures whether the CO2 is utilized or it is less utilized. Obviously, if a plant is under photosynthesis, so CO2 will diffuse through stomata into the, if you are providing actinic light, then the CO2 will be fixed. It will enter through bicarbonate. It will first enter into the stomata, then convert into bicarbonate, then through bicarbonate it will be fixed through C3 cycle or dark reaction. So that dark reaction, Rubisco activity plays an important role. Okay, so this does not exactly measure the oxygen evolution or anything, because this already I told you, this is a only measurement for heteroatomic molecules, heteroatomic gases, not all molecules, heteroatomic gases. So it will measure only the CO2 concentration. So CO2 concentration, it will see if a plant is performing well, the CO2 absorption will be more or less. Then with the CO2 absorption, it will link all other things. Stomatal conductance, if a CO2 is more absorbed, then it will calculate its stomatal conductance based on its internal calculation parameters. Then comes your transpiration rate. Then from transpiration rate, you can go for net CO2 assimilation. Okay, CO2 assimilation, that is represented by AN. AN means assimilatory rate. Got it? So these are 4 or 5 basic parameters that you can get from IRGA. Apart from that, you can go for ACI curve. ACI curve means, A means already I told you, assimilation rate. Okay, so in x-axis this will be assimilation rate, in y-axis this will be your internal CO2 concentration. Got it? So usually what is the atmospheric CO2 concentration in ppm?
300 to 410.
Around 400. Got it? So atmospheric CO2 concentration is 400 ppm. So if we increase the CO2 concentration or you decrease the CO2 concentration, okay, what will be the effect of plant if you want to check? For example, if a plant is growing continuously under 400 and again you are shifting it to from 400 to higher concentration, let's consider 800 or even 1200 or 1600 or 1800 ppm. So that way how the plants are behaving. Okay, and again in the higher concentration to the lower concentration, how the plants are behaving, you can measure through this method. Got it? So if you have any stress kind of plants, and if it is related to your CO2 uptake, how the CO2 fixation is there, how the stomatal conductance is operating, how the net CO2 assimilation is there, how your Rubisco activity, how is it happening, that can be measured directly from this. Actually, ACI curve, through ACI curve, you have to first, I'm not going in details with the ACI curve, because if I start ACI curve, it will, for one sample, it will take at least 45 minutes. Okay. So first of all, for taking IRGA curves, it has to be, the leaves has to be always connected with your plant. Once it is detached, the water content will drop. And once the water content drops, everything else will be hampered. Transpiration rate, stomatal conductance, net CO2 fixation, everything. Because ultimately through stomata, the water vapor evaporates. So if the water vapor is less, or if you are plucking it, the plant leaf is having a molecular mechanism that it will close the stomata to just prevent the water loss. So once the water loss is less, you will get faulty readings, because stomatal closure will be there. Once the stomatal closure will be there, CO2 fixation rate will also drop, and also net CO2 assimilation will also drop. Got it? And similarly, because stomatal conductance is directly correlated with your transpiration rate, that will also drop. Got it? So this thing, one thing you need to be always clear is that the leaves should be always intact with the plants. That is in vivo measurements. Right now, I don't think IRGA has for algal samples, but for leaf samples, you can do it. Got it? So, any doubts up to this? So how does it measure? First of all, we have to give a reference CO2 concentration. You got it? So it basically measures your CO2 concentration. So if we give a reference CO2, for example, the atmospheric CO2 concentration is 400 ppm. So we'll give you a reference CO2. Okay. From the reference CO2, if a plant absorbs some amount of CO2, if a plant absorbs more CO2 concentration, if a plant absorbs less CO2, then the reference CO2, comparing to the reference CO2, we can know how much the decrease is there. And depending on that decrease, we can say the plant is performing well or it's under stress or any kind of thing. Got it? So first, you need to, so for general photosynthesis, what is needed? Normally, what is needed? Normal photosynthesis. CO2, then O2 is actually not needed. O2 is required for respiration. For just photosynthesis, what is needed? First of all, water. Okay. Pigments, already it's done. Pigment protein complexes are there. Then what is needed? Solar light or light, actinic light. Okay. In the form of, in nature, we get it from solar energy. So this exactly does the same thing. So already you have the plants. Okay, plants, already the water, everything is there, the chlorophyll. Only thing, because we are performing through manual method, we have to provide a light source. Got it? There is no need of dark adaptation because we are not measuring fluorescence. Okay, so fluorescence, because we are not doing, there is no need of dark adaptation. But to stabilize the readings, it will take like 4 to 5 minutes. Okay, for one reading to stabilize. Normally within 3 minutes the readings get stabilized. So this part is your chamber, IRGA chamber. Okay, so here you see there are two points. Okay, one will be for reference and one will be for sample. Okay, reference and sample CO2 difference will be reflected in this machine. Reference will be a constant CO2. Usually if a plant is constantly grown in 1400 or 800 or lower CO2 concentrations, even 200 or 100, that will be the reference CO2 concentration of that plant. Got it? If it is grown continuously from the starting point. Okay. So if I got this from outside, so outside the surroundings, what is the CO2 concentration? 400 ppm. So we have to keep here 400 ppm. Until and unless you want to check how the plant is performing in very high CO2 or very low CO2, the ambient CO2 or the plant condition in which the CO2 is there, whatever the CO2 concentration is there in that ambient condition or in which the plant is grown, that is taken as your what? Reference CO2. You got it? And sample CO2 will be based on the plant's photosynthetic performance. So sample CO2 will never be higher than your reference CO2. Remember this. Sample CO2 can never be higher. You are supplying 400 ppm. So will it go 500? It can never go 500. Only the CO2 has to be utilized. The utilization might be less or the utilization might be more. If it is less also, it is never, at least 400. 400 is also very uncommon. 400 means the plant is not at all fixing anything. So it is under huge stress or might be the plant is dead. Okay. So just remember one thing, reference CO2 concentration is always higher than your sample CO2 concentration. Okay, that is internal CO2 concentrations. Another thing what you need to do is, these two are for, one is for reference CO2, one is for sample CO2. Now how we supply CO2? We supply CO2 with cylinders. Okay, these CO2 cylinders, we use it to supply the sample CO2, sorry, reference CO2 concentrations. Why this 12 gram CO2 cylinders we use? Usually it will last for 9 to 10 hours. Then you have to discard. Whether you do the experiment or not, the CO2 will be released. Got it? So once it is punctured, it has to be used in one go. So if you want to repeat the experiment tomorrow, you have to use a fresh CO2 can. In some people who can't afford this CO2 cylinder, these are very costly, around 500 to 700 per capsule. So if you are not going for this, there is an other way, but in that condition you cannot go for high CO2 concentrations. It will get the ambient CO2 concentrations. So for ambient CO2, if you are using ambient CO2, there is a hole here, this one. You can come here and see, or else this one. Okay, so if you are not using this CO2 cylinder, you can directly put a pipe here. Okay, and that pipe you can put in a thermocol box. And why in a thermocol box? So that there is no pressure fluctuations. Okay, air pressure fluctuations, if it will be there, then CO2 will be more or less. So we have to just maintain the whatever the pressure is there. So that's why you just connect it to a thermocol box and just cover it slightly, just open the box and it will maintain your ambient CO2. But if you want to go for very high CO2 concentrations, more than 400, 600, 800, 1200, then 1600 or 1800, then you can't go for that. For that you will need this one. Got it? That is the reason we use this one, because we use both ACI curve as well as APAR curve. APAR is CO2 assimilation and PAR is photosynthetically active radiation. So with respect to PAR, your CO2 assimilation will be plotted. APAR. A is in y-axis, PAR is in x-axis. Similarly, ACI is A is in y-axis, CI is internal CO2, that is in x-axis. Got it? So first of all, we need to puncture. Got it? So before that, we need to fix this chamber with the analyzer. So this is basically the analyzer. The name is Lycor. Okay, Lycor, and the system is 6400XT. Okay, and this is a portable photosynthetic system. There is another system, more developed one, that is Lycor 6800, and that is more portable than this one. Got it? So this part is your analyzer and this one is your IRGA chamber. So what does the chamber consist of? The chamber here, if you'll see the top here, LED source is there. Okay, apart from LED source, infrared radiations are also applied. Got it? Why the infrared radiations are applied? I already told you, it has to detect the heteroatomic molecules, that is the CO2. Okay, only CO2 it will detect. So once the CO2 is there, whatever CO2 levels are inside this chamber, it will compare with the reference CO2, and then if it is dropping, then how much drop is there, that it will calculate and show it here. Got it? So LED source is over here, and there is a small wire like thing that will maintain the temperature of the leaf. Okay, because leaf temperature is also directly proportional to your stomatal opening and closing. Got it? So you want to make sure that the leaf temperature does not fluctuate too much. Okay, so these are all the gaskets. You just have to place your leaf here and close the chamber. So for closing, usually to avoid damage to these gaskets, we loosen this when we store it. Loosen this means there will be some gap, okay, between the gaskets. So while using it, make sure you just tighten the gaskets first. So to tighten it, just turn it around. Yeah, it is more or less tight. Okay, so once it is tight, you can just go to any light source and see whether there is light leakage or not. It should not be too much tight. If it is too much tight, then you will damage the leaves. Okay, and it should not be loose. If it will be loose, then CO2 will escape. Your reference CO2, whatever you are maintaining, it will escape. Got it? And there is also a light detector. This is the ambient light detector. Whatever the light means PAR intensity is there in the surrounding, this will detect. Okay, and apart from this, these are all to cool down everything. LEDs are there, these are all the fans to cool it down. Just these are your basic things. Okay, this is the main chamber. This is for your one is for your reference CO2, one is for your sample CO2. Got it? So once this chamber is done, this part is your analyzer part. Okay, so this is the main component. Here all the analysis part will be done and everything will be recorded here only. Got it? So first you have to connect this with your chamber with your analyzer. So for this there is cable. Okay, yeah, you can use it. So here you see there is a black colored mark. Okay, so this black colored has to be matched up with this black. Otherwise, if you will mix up with reference with sample and sample with reference, all readings will come faulty. Okay, so first thing you have to do is to fix it. And another thing is that these gaskets, once these gaskets are damaged, you have to replace it, because if you will not replace it, the CO2 will leak, and once the leakage will there, again the readings will come faulty. Okay, so by the time he fixes, I will tell you what exactly this fix. Okay, so this is your main analyzer part. So here the CO2 cylinder goes. Okay. See here, there is a rubber gasket. If this gasket is even damaged, you can remove it with the help of, there is a prong here, just you remove and you can insert a, typically after every 4 to 5 readings, you have to change the gasket. It's not damaged, so you can just see whether the gasket is damaged or not. Just physically you can see whether it is not damaged now. Okay, I replaced it recently, so it is not damaged, but typically 5 to 6 readings or even 2 to 3 days you have to change the gaskets. Okay, so you just put it inside. So I will just loosely tighten first. Once these are connected, then I will tighten it, because there is also a chance to the CO2 leakage might be there from this way. Okay, so I will just loosely tighten it. Now the puncture is not there. Once it will become tight and you have to give a final tight one. That time the puncture you will get a very small shush kind of thing, like air escaping, you will get some kind of thing. Okay. So apart from this, there are two. These two are, one is your dryite and another one is your soda lime. Okay. So if you are using CO2 can cylinder, it's basically first this CO2 is under huge pressure. Got it? So a gas under huge pressure becomes in liquid phase. Okay. So gas under huge pressure, it comes under liquid phase, basic physics. So now if it will release at the same time, some amount of liquid water vapor will be there in it. Okay. So yes, moisture will be there. So in order to remove those moisture, you have to scrub it. Okay. So for scrubbing, you have to use what? Not silica. We don't use here silica. We use here soda lime. Got it? Soda lime. This one. We use this one, and for dryite to dry out whatever the another thing. This color of dryite you see, which color? Blue color. Once it becomes dry, once it becomes moisturized, it will turn to pink color. Okay. So once it completely turns to pink color, you can't reuse it again. You have to again heat it. Okay, heating may be done for 3, 4, 5 days at 100 degrees in oven. Okay, after that all the water vapor will evaporate. Many labs do that if they can't afford to buy every time. Okay, so you can reuse 2 to 3 times, not more than that, if you really want to. Okay, so these are the two things. First, let him connect. I will tell you. This is your soda lime. Soda lime is here, you see. CO2 scrub is there, na? Here you see what is desiccant. Desiccant will basically, it will your take surroundings, it will have water vapors in it. Even this one also. So it will dry the air. Only CO2 will be taken out. Got it? And this is also to remove whatever the moisture is there. Just to clean the air to get pure CO2. Okay? The function of these two is to clean the air and to get pure CO2. Connected? Okay. So see this connection, keep it well. Okay, you see, one is your just the basic connection. There is no big deal in it. First, these two connectors will not interchange over there, because only one connector is that side and two connectors is here, and one is female, one is male. So you will not confuse which connector is what. Got it? So these two are for just to connect all these things. Light source is there, fan is there, to everything, to connect everything. These two are there. Right? So now you see these two pipes. These two pipes, one I told you, it has to be same for everywhere. There are also two pipes. Here also two pipes. One is for reference CO2, one is for sample CO2. The protocols you have, na, that is shared. Protocols is not shared. Okay, we'll share it. So once this thing is done, you have connected everything. First you have to do is to So this is actually a portable system, but it is actually very heavy. So anybody wants to just try how heavy is it, they can try. So this is just your this purpose, okay? Maybe more, 15 maybe, and if you will include these and batteries, it will be more than 35-40 kgs. So put it inside, no? Put it inside. So batteries, these are rechargeable batteries, okay? So depending on what work you are doing, it will last for max to max 3 hours, okay? So if you are doing general parameters, it may last for 4-5 hours. But if you are taking ACI or APAR curves, like 6 to 7 readings, if you are taking in a day, they will last for 2 hours max to max, okay? So some people, they use direct AC source. So you can connect in these two batteries, you can connect a AC source, but the connector has to be this type. Got it? So once you switch on this, pull over these batteries, then switch on the instrument. After you switch on, the initializing program will start. Okay. Okay. Once you start it, the 2x3 LED light source, you have to connect it. Okay. Not the factory default. So 2x3 LED source is because of 3 centimeter in 2 centimeter. This one. Okay. The size of this one is 3 centimeter, 2 centimeter LED source. So you have to first connect it. So you just select. Okay. Now it's asking, is the chamber or IRGA connected? This is the chamber of the IRGA. So first of all, you have to make sure it is connected or not. Just make sure everything comes. Okay, there is a black ring around it. So this will go with this one. Got it? There is no black color anything, just a ring around it. So that means, okay. So you just press yes, Y for yes, and for no, if it is connected. If it is not connected, then you have to press no. So you see the sound, some click click sound came, right? This is the mixer. So it will just test if the mixer is working or not. Mixture, what happens if you use this CO2 cylinder, it will mix this CO2 with some of the atmospheric CO2. It will not utilize everything. So that, with the help of that, this mixture operates. Got it? So if it starts to utilize CO2 everything here, maybe it will not last more than 1 hour. Okay, that is the reason this CO2 mixture is done. Now this thing has started. You will hear a fan sound.
But then the concentration may differ.
Why? No, we have to give a reference CO2, na? It will adjust accordingly. If you are giving 400 ppm, see 400 ppm we don't have issues. If you want to go for higher ppm, 1800. So the atmospheric CO2 is 400, right? It cannot go to 1800. So it will take some of the atmospheric CO2 gas and again it will mix the CO2 from here. This is complete CO2. Okay. So here, and it is under pressurized form. So you just pressure some amount of CO2 it will take from here and some 400 ppm from outside. It will mix and make it up to 1800. Got it? This is the reason this mixture works. So when you will start the IRGA, if the mixture is working properly, this click click sound initially it will come. If it is not working, then the mixture will not work. Okay. So once it has started, I will start to puncture it. So it is done. Okay. So the puncture is done. Okay. Now what you have to do? First, if I take any light intensity, for example, if I take 200, so will I be able to get a maximum CO2 assimilation rate of this plant? No. Why? Why? No, it's not our reference CO2. Let's keep reference CO2 as 400. Okay. So if I start to give a 200 microinstein light intensity and I record the readings, there will be some readings in 200. So will it be the maximum CO2 assimilation rate of the plant? No. Why? Why? I told you already, maximum CO2 assimilation rate. Maximum CO2, you know the law of limiting factor? What does it mean? Means? Yes. Not reagent, anything can be lower. Yes. Any component, whichever is lower, that will directly affect the product. Okay. So now, if the plant is already grown in 1500 microingstine, 1200 microingstine, and you are giving rest all the parameters same, CO2 you are keeping same, relative humidity you are keeping same, light apart from light, but light you are giving 200. So will it show the highest CO2 concentration? It will not show, because it is already grown in 1500. So for that you have to go for APAR curve. APAR curve, once the curve will come, there will be a point in which there will be a drop. I will show you how the APAR curve is plotted. So every plant will have a saturating light or PAR intensity. If you go beyond the saturating PAR intensity, there will be photo inhibition. If you go lower to the saturating intensity, it might be limiting. Limiting means the plant might not be performing to its full potential. Got it? So that's why you have to first give a saturating PAR to the leaves. For that, you have to determine which is the PAR. Got it? Which PAR intensity should be given. So for that, you have to first perform a PAR curve. Okay. So for a PAR curve, you just have to press here 5. Okay. Just press here 5 directly. Sorry, you go to new measurements first. First will be new measurements. Okay. So once the new measurements will come, this thing will start. Okay. Then you just press 5. Okay. From here, another thing, before running, you just see these readings. See these readings. So you see CO2 reference and sample. Did I switch on the mixture? Nothing. I didn't give any values of CO2. So everything should be, that means leaves are there inside it, no leaves are there. So it should come around 0. Got it? So photosynthetic rate before starting, this should be around 0. You have to wait for 5 to 10 minutes until this warms up. So it will take like 10 minutes to warm up and it will come around 0. Around 0, it may not be exactly 0, 0. It will be around this kind of it will increase and it will decrease. Got it? So for that, until that time, you have to stay. If it does not come to 0, then you have to again recalibrate it. Okay. So if it is required, I will tell recalibration. If it is coming to 0, then no need of recalibration. So you just wait for 10 minutes. So make sure that this is closed. So see the difference if I open it. Just see CO2 reference and CO2 sample. Okay. So if I just open it, see the sample CO2 concentration. Got it? Then this CO2 concentration is increasing. Okay. So you have to use it first. So how do you know at what time it is getting stabilized? The photosynthetic rate should be 0, around 0, 0.01 something, or minus 0.0, that is also fine. But it should not be 1 or 2, 3, it should not be like that. So first there row. The first row is okay. Second one is CO2 sample. So another thing is that before taking any readings, we have to match the CO2 reference with CO2 sample. But before matching, we have to wait until the IRGAs become warmed up. Okay, it will take like 10 or 20 minutes to warm up. After this, you can matching. Okay. After this matching, this is your water reference and this is your water sample, and this is your change, net change. What is the change in reference and sample? Here it is reflected. Okay, it should not be negative because we have not kept any leaf and this is not calibrated. That's why it's showing negative. Okay, once it comes to 0, this one will come around 0 also, and this is your also change in the water, this too. Okay, these most of these two will be same, but major thing we have to calibrate this two. Reference CO2 and sample CO2 has to be same. Then this is the flow, relative humidity should not exceed 75%. And then transpiration rate, this is internal CO2, this is conductance, this is net CO2 assimilation, okay, photosynthetic rate. So I think that's fine. Okay, so you see now the readings are more or less stabilized. 0.41, 2.42, it's not that much. It's not going 3.5, 3.7. It will come like that. If you want to go for graph, you just press this end. Just you press this. Here you will see. Here the saturating point is already reached. This point. It was increasing. Then the saturating point has reached. So now you can know that readings are more or less stabilized. Got it? So you just press escape. Once you press escape, it will come back to your main menu. So it's 2.45. So it is not calibrated. So first we have to do is again calibrate it. To press again. Okay. Then menu. Okay. Then you go to IRGA. Then you go to. Then press enter. And closed, okay, and total desiccant, it's like 4 or 5 times it has been used, so it is fine. Okay, now we have to press Y to continue. So then again it's asking the chamber must be closed to 0, CO2. Press any key. Everything is mentioned here, no need in too much, because it will be whatever the readings will need, it will in here. So you have to press any key, just press any key. So it will take some time to zero the IRGA. Okay. So these two readings should be around same. It may not be 0, but the reading should be same. So what do we have to do? We have to make this 2 sample as 0. Okay. So initially when you will wait, this readings will stabilize. It will be minus 5.5, 5.6, 5.7. It will be 9.1, 9.2, 9.3, 9.4, this kind of thing. So after that, these values are a bit different, right? Then you have to zero this. Zero this means these two values will come to closer to each other, very close to each other. Okay. So you can just go to CO2 reference sample 0. CO2 RS means R for reference, S for sample. So these two things you want to make it to 0. Got it? So you can just go here. So it's not changing much, you see, 9.2 to 5 minus 5.6. You just press F1, just the beneath this button. So setting 0 low, setting 0 high, then it will make two values almost similar. Okay, now you see. So the reference and sample CO2 is around 0. Okay, 0 0.0, 0 0.0, around minus 0 0.0, 0 0.1, even sometimes it happens. Got it? So once this is calibrated, you have to quit. So now if you want to just press escape, again you go to new measurements, then you see these values will be almost similar. Okay, so now reference CO2 and sample CO2 will be, and here also the photosynthetic rate will be, should not exceed more than 2 or 1. Got it? So again you have to wait for like 5 or 6 minutes. So if you want to really check what is the plot, just press this one and it will show the plots thing. So until and unless this line comes in a straight line, so that is the saturating point. If it is dropping or if it is increasing, then you will know that this is not the proper time to record the readings. You have to wait until these readings stabilize. Okay, not saturate, stabilize means it will come in a almost more or less straight line. So almost it has stabilized you, so it's not changing too much. This is also a bit straight line also. Okay, so you see the range is from -1 to 0, so it's very less range. So it is straight line only. If you just compare from 0 to 100 or 0 to 50, this will be completely straight line. Got it? So now once the IRGAs have warmed up, just go to escape. Okay, so also you see the photosynthetic rate has not changed. Got it? Now we have to go for APAR measurements. APAR will determine your maximum photosynthetic active radiation. Okay, so you don't want to give a light that is photoinhibitory to a plant, and if you don't want to give a light that will record or down record a photosynthetic rate of a leaf. So first you have to measure the exact PAR intensity. So for that you just press 5. Okay, then you go to auto program. There is an auto program based on it. So you go to a light curve 2 here.
5 or F5?
5. After F5 there will be direct how to, I'll show you again. Just go to 5. This is 1. Okay, 2 comes this one, 3, this is 3, this is 4. Okay, this is 5. Got it? So before going to 5, let me tell you one thing, since I'm browsing everything. So you leaf fan will be fast. This fan will be fast. So flow is 400 micromolar. Mixture is off. Now mixture, since we use this one, we have to give how much? 400 ppm. So we have to add the mixture. So reference U2 is already, it is set as 400. Got it? So you just keep means it will keep this thing. Got it? So reference U2 is 400. So temperature is off, lamp is off. In APAR, the lamp will be automatically it will start from highest intensity and it will go back to lowest intensity. Got it? So you don't need the lamp because you have not decided which is the PAR, exact PAR. Got it? So it will automatically increment from 1800 or maybe 2000. From 2000 it will start to 1800, 1400, 1200. That way it will check at what intensity there is photoinhibition and what intensity is the perfect to take the readings. Got it? So you just press, now you press 2. This is the second one. Okay, so if you go to 3 usually marks the area of the leaf. You have to give either you can take a graph paper to plot the exact area, or else you can averagely calculate it. Maybe it's not 6, so I may write it as let's say 5. Okay, 5 centimeter square, then press enter. This is a average one I'm taking, this leaves. Okay, so apart from this is 3, this is 4, this is 5. Okay, so this point you need auto program. So once you go to auto program, click it, then light curve. So after you press the light curve, we have to give a name of the file. Okay, so first I am giving a name of the file, APAR space DEMO 1 space, okay, demo, just write GMGIA. Okay, so this is your file name. Okay, APAR demo GANT. Just you press enter. Okay, a remark you don't need to write. Press enter. Now you see the summary is 12 points. Okay, 12 points means the light will be decreasing from the highest intensity to the lowest intensity in 12 decremental values. Got it? So the first value will be your 1600. Okay, 1600 PAR will be your first PAR intensity, and the next PAR intensity will be like check. Okay, so first PAR intensity will be your 1600, then comes your 1400. This you can adjust manually also. You can change here if you want, but it has to be which one? First PAR reading also you can change, but usually it will not go beyond 2000. 2000 is more than sufficient PAR reading. The sunlight is around 1800. No, you have to determine a PAR. Let's say example, if I just write 1800 here also, it will start from 1800, then 1600, then 1400, then as long as you get a saturating point, there is no problem. If you don't get a saturating point, you may increase the PAR, but maximum it can handle 2000 because the sunlight's PAR intensity is 2000. Got it? around 1700 to 1800 natural sunlight. So it starts from 1600 par, then it goes to 1400, 1200, 1000, 800, 600, 400, 200, 10, 50, 25 and 0. Okay, these are all the par readings. So you just go to escape because I didn't change anything. So each point will last for around 180 seconds. 180 seconds means consider like more than 2 minutes. 2.5 minutes, how much is 183 minutes? 3 minutes. So max to max it will take 3 minutes. Within that it will take a point. So each 12 point means 1 point is 3 minutes. Understood? So you just do 12 into 3. How much? This is just for taking one readings. So you have to wait for 36 minutes to check the exact par intensity that a plant is performing well, or a photoinhibitory radiation, you can know. Okay. So we'll just start it. Once you start it, before starting, you have to keep the leaf. Suhail, bring that one. There is tissue now. And make sure you wipe the leaves. Otherwise, yes, because of the dust, it should be fine.
They don't like water if they have.
Water content is also there, na? Means it will directly affect your transpiration rate and everything. So just slightly just wipe the leaf. So while placing the leaf, make sure that the leaves does not fold, okay? Because if the leaf folds, your values will come different. Single leaf, it should not be overlapped. Okay, so you can start it now. Just wait for 3-4 minutes, or else you can start the readings. Okay, now the reading has started because this star mark you see, it's blinking. Okay, this star mark you see, it's blinking. First 2 seconds it will blink. By the time you saw, it stopped. So you see now the photosynthetic rate will be in positive side. Okay, so it's coming to like, it will record. It's not stable yet. So if you want to really see at what point it's coming, what, just press this one. So it is still not stable. You have to wait. So just to view the graph, you press this one. Okay. 5 star means sometimes it's blinking, na? That means the program is running. Okay, so this now it has almost stabilized. Okay, now you have to go to scroll these things and go to your this one. Okay, A par, this one you have to go. Now it is around 1600 around. So the photosynthetic rate is very less. Why? Because we shifted from a lower CO2, outside CO2 is 400 to here, that is very high. Okay, that time I opened and show you, right? It was around 1600. So that might be the reason the stomata is closed. Okay, but usually natural conditions, it should be around 4, 5 something it should come. Okay, so now if you want to see what point it will come, so you just wait until 3 minutes it will take, and it will go to 0. Definitely it will go to 0, but you have to wait until whatever point it drops below 0, that will be your compensation point. Means beyond that, if you give light, the plant will photosynthesize. Below that, the plant is not able to photosynthesize. Got it? Because the CO2 inside this, we got it from outside to inside. That was a shock for the plant. So usually it is ideal for the plants to take where the plants are grown. Just for demo purpose and this video filming, I got this inside room. Got it? Another thing, at each point, whenever the plant takes a particular condition, this point is recorded, right? Okay, this point is recorded. Now we don't know 1600 might be photoinhibitory or not. If this point is higher than this something 1 or 2 does come initially. If it is higher, then it is not photoinhibitory. If it is lower, then it if it is higher, then the next point is photoinhibitory. Let it run. I will tell you the graph you can get. So this was your 1600 power, 1599 written, right? So last power we gave is 1600. So now the next power is running 1400. It's running now. Got it? So until 3 minutes, it will wait to see the readings are getting stable or not. After 3 minutes, it will take the readings automatically. And every readings is followed by a what? Sampling of the water and CO2 reference. Equalizing the CO2 reference and sample, every reading has to be done. So this is the basic idea. The actual photosynthetic rate will go beyond 10, 11, 12. Okay, if the plant is in native place. If you shift the plant somewhere else, then for maybe for temporary time, it will close its stomata because you're shifting from low CO2 to a very high CO2 here. Got it? So that might also stress out the plant. So the second reading is taken. You can see here the CO2 reference and sample is almost same, 400 ppm. Okay, so these two readings are already taken, these two, and it is very low. So if you can see, this point is slightly lower than this one, right? Slightly lower. So 1600 is your photoinhibitory, at least till here. We don't know about this point, what is going to happen, but this one is 1600 is definitely photoinhibitory. So we have to wait whether this point is higher or not. If it is higher, then this point is also photoinhibitory. So you have to take this point. So again, if previous power intensity is higher than this, then this point is also photoinhibitory. So you have to see what point is your photoinhibitory point. So you have to take that point which is not photoinhibitory and which gives a highest point. Okay. Okay, you can sit. By the time it will take it will plot all the graphs. Okay, a lot of time. APA they have to do first. We got in inside plants. We got the plants inside. The CO2 concentration is very high. Inside, people are here, na? That's why it's giving very less for the take rate. Pressing no. it will ask, we'll be continuing on, but before connecting the IRGA, put the Li64 into sleep mode. Sleep is found in until menu. Okay, so no need of doing, just press enter to it. Just go. So again, it will now come back to the main menu. Connected, na? Okay, so first you have to connect here L term. L, you have to press L, then you have to press your T here. So first press your L. So once you press L here, it will be shown as L term. In the home menu itself, it will be shown L term. Now just open this one, LI6400. This one, T is written, right? Open this. Then you have to select which connection is needed, because this one is RS232. It's not Ethernet cable. Okay, you have to select RS232. Okay, and only one communication port is available here. You just go to connect. Okay, now this is your IRGA. Whatever the IRGA is here, it's displayed here. Got it? It is just mirroring whatever things are here over there. So now you go to that. Yeah, you have to go to files. Okay, so right side you see there is a plus sign here. Got it? Just click on it. Then go to users. Again press here. Okay, once you press on users, all the files will come. Okay, whatever name you have given. So I'll just browse and see whether today. Okay, here you have to only take the .xls. Okay, so you just take it, drag it and drop it in whatever position you want. I dropped in downloads. Okay, and apart from that, I don't know whether the other thing recorded or not. Okay, I am taking another one to show what exactly how it should look. So here 60% you are seeing, right? 80%, that is the transfer file. So once it is done, you can go for next. So just for showing purpose, I am just taking one of my files. And this one also, I'm taking one of my files. So only .xls is the Excel file. It can only open in Excel file. Other files it won't open. So you just copy only the .xls files. Okay. It's not increasing to 4. Okay, it should increase. It's not increasing. Okay, once it is done, just close the file. Then you go to disconnect. Okay, just go to disconnect. Once it is disconnected, you can close the software. Yeah, and after that you just press again L, so that L term will disappear now. And then you can switch it off. So now coming to the plotting thing, I'm showing how to plot. Okay, it's corrupted. Maybe okay, the file is somehow corrupted because I stopped. Anyway, I'll be showing you how the file looks like, exactly how the Excel file looks like. I have one of the Excel files. GS is your stomatal conductance. Just divide 13.575 divided by 0.29. Okay, so whatever value it comes generally goes with your supplementary data. Okay, so the reviewer might ask why you have taken this per intensity, why not more or why not less. So that way you can show that at this point the highest for that, if CI is less, then the plant is good condition or not. You have to check along with it the stomatal conductance as well as transpiration rate. Obviously two things go hand in hand. One is stomatal conductance and another one is transpiration rate. If stomatal conductance decreases, transpiration rate will decrease. If stomatal conductance increases, transpiration rate will also increase. Fine. Okay. E is your this one, transpiration rate. Okay, E is in paper format. E is represented as transpiration rate. Ga is stomatal conductance. Ci is internal CO2. An is your CO2 assimilation rate, and WUE, that is A divided by GS, is your water use efficiency. Okay. X-axis depends on whatever conditions you take, wild type or treatment plants you can take. Okay. Okay, I think this is done for today. Anyone has any doubts? Okay.